Okay, welcome back to Calculus. In Chapter 9, we're going to be taking a look at a subject called differential equations. We're just going to kind of scratch the surface of this subject. You can take entire courses in it here at Humboldt State University and elsewhere. Differential equations are, from a scientist's point of view, I think sort of why we study calculus, because as you'll see, differential equations are equations that involve unknown functions and their rates of change. And rates of change are basically things you can observe. So my kind of generic definition of what a scientist is a person who observes things, observes rates of change, through those observations discovers relationships about the rates of change, and then they want to use that rate of change information to be able to predict the quantity. And then, what the quantity is depends on what kind of science you're into. But mathematically speaking, most scientists are interested in solving differential equations. Okay. So what I want to accomplish in this first lecture here is mainly just some terminology. Introducing some terminology, I want to tell you what a differential equation is. I'll denote them by dE for short everywhere. I want to tell you what I mean by a solution to a differential equation and what I mean by an initial value problem. We'll practice some skills with these terms. Given a specific function, I want to be able to determine if it's a solution to a given differential equation. And then I want to be able to find certain values of constants that satisfy something called initial conditions. Okay. So often these solutions to differential equations will be families of functions, and you want to identify a specific member of that family by plugging in a certain kind of a condition, a specific point on the graph. Okay, so that's our goal. Let's just get going. So the first slide here, I've got it all written out just with the definitions. You can stop the video and kind of absorb it at your own pace. But by a differential equation, so a differential equation, which again, I'm just going to be denoting everywhere in the lecture here. I should have done it in this slide already, but by its acronym DE, its initials, it's just an equation that involves some unknown function. So this is what's kind of different about it, is the unknown in this equation is not a number. It's not equations like 4x equals 8, where you're trying to determine a value of x that makes that equation true. The unknown in a differential equation is a function, okay? And the equation involves that function and its derivative, or maybe more, second derivative, third derivative, it depends, okay? And you can also have in the differential equation other functions of the input variable, the independent variable, whatever it's called. On this slide, I'm calling it x, and often it's called t because in many examples, the independent variable is time. All right, so I've got three examples of differential equations written here. Each one of those things is a differential equation. So I have an unknown function. I'm denoting it by y of x. Let's look at this first one together. And this equation says that the derivative of y of x is equal to 6 times y of x. All right, so you can find a solution to that equation if you can think of a function that when you differentiate it, you get 6 times it. That's what the equation is asking. I'm not talking about what the solution is here. I'm just talking about differential equations. Okay, here's another one. In the second equation, the unknown function satisfies that its derivative is 1/10 the difference of it and 130. Okay, so I'd be looking for some function that when I replace that function in this equation right here, and I replace its derivative right there, I would want the expression to be true for all x. Okay, so I'm kind of talking about what's written down here on the bottom. A solution to a differential equation is some function of the input variable that when you plug it in, along with all of the relevant derivatives, and in these equations that I've written up here, the derivatives are first or second order, it has to satisfy the equation. And by that, I mean for all x. So I have to get some equation after substituting that would be true regardless of the input variable. Okay, so that's what I mean by a solution. This last equation, I shouldn't leave well without talking about it. It's the differential equation, some unknown function, second derivative plus 17 times it is equal to 0. And maybe lots of functions. You should stop the video right now. You think you could produce some solutions to that? Don't worry about how, but maybe just try this first one. Maybe just try this first one. Do you know a function that when you differentiate it, you would get 6 times it? I'll bet you do. I'll bet you do. Okay, so there's some of the terminology. Let's look at an example. I'm going to pick on that first differential equation. Maybe this is what you came up with. So we're just being asked, verify that this thing So we're given y equals 6e to the x. Verify that it's a solution to that differential equation. Here, and I'm going to do this a lot, above I was writing y prime of x and y of x, but a lot of times when the input variable is understood, what its name is, we'll just shorten the notation and write things like this. Y prime equals 6y. So I don't mean anything different like when I was writing above, y prime of x equals 6y of x. I mean the same thing. It's just sort of a lazier way to write it, if you like. Okay, so what does it mean, verify this is a solution? Well, the slide above here, we can even look at it while it's kind of far up there, but what I need to do in this case is take my proposed solution, y of x, it's e to the 6x, and I need to just differentiate it once because there's only one derivative in the equation. So I'm going to replace this y prime with its derivative after I calculate it, and then I'm going to replace this y with, well, e to the 6x, and I'm going to see, is that expression true for all x? I think you can probably already see it is. So if y is equal to e to the 6x, then its derivative, y prime, is, well, by the chain rule, it's e to the 6x times 6, or that's 6e to the 6x. Okay? And you can see, I'm just going to kind of continue forward here. That's 6 times y, right? Because e to the 6x itself is y. So instead of plugging in, I've just kind of derived it. So what did we learn from this computation? That the derivative that we just calculated is in fact 6 times y. So that shows that y equals e to the 6x is a solution to the differential equation y prime is 6y. Okay, let's continue. There's another solution. Solutions to differential equations aren't unique in the sense that there's not just usually one function. I claim that 16 times e to the 6x is another solution to that thing. Right, so we can kind of crank that out. Let's just differentiate. What's the derivative? Well, it would be 16 times the derivative of e to the 6x. That's e to the 6x times 6. And I can write that as 6 times 16 e to the 6x. And then again, 16 e to the 6x is exactly y. So that 16 didn't ruin it. At the end of the day, I also got that this function's derivative is 6 times its value. All right. So more generally, we could take any constant, c, and multiply it by e to the 6x, and it's a solution to this differential equation, y prime is equal to 6y, for any constant c. Okay, I'm going to leave, well, let's just verify it real quick here. Y prime, differentiating, you leave the constant out front. The derivative of e to the 6x is e to the 6x times 6. That's c times 6 times e to the 6x. That's c times y. Okay, excuse me. I don't want to edit the video this deep into it, but I did make an error there. I want to rewrite that thing as 6 times c times e to the 6x, and now I see that that is 6 times y. Sorry about that. Okay, so this thing, y equals c e to the 6x, is called the general solution. The general solution. Oh, it's not going well here today. General solution. It's the general solution because it involves this arbitrary constant. Okay, so the values that I chose in my first two examples were c equals 1 and c equals, I forget, 16. Those were particular solutions. So the general solution is identified by the fact that it has this constant in it. Okay, some more terminology. Let's practice a little bit more here. Same kind of example. I want to show that y equals sine 3t is a solution of the differential equation y double prime plus 9y is 0. So here the input variable is not called x, it's called t. Okay, but that's okay. It doesn't matter what the input variable is. In order to verify this, for this one, we have to twice differentiate the proposed solution because I have to plug in the second derivative. And then I'm going to add 9 times the function itself and see if I always get 0. So let's start by computing a couple of derivatives. The derivative of sine of e to the 3t, I'm going to kind of pick up the pace here and say by the chain rule it's cosine. And so the second derivative is, well, minus 3 times 3, that's minus 9, and it would be back to the sine. So you can check my differentiation. So this time, maybe I'll do it more in the spirit of plugging in. So if I take y prime prime plus 9y, and I replace y prime with what we just computed, and then I add 9 times y, well, y is the sine of 3t, I think that you can see that no matter what t is, that's equal to 0. Okay, so that shows that y equals sine of 3t is a solution. Just trying to get you used to the terminology. It's a solution to the differential equation y prime prime plus 9y is equal to 0. Okay, I wouldn't call it the general solution because it doesn't involve any constants. Nice. Let's do another calculation here real quick. Let's show that y equals cosine of 3t is another one. Same differential equation. So let's just do this quickly here. So y prime this time would be minus 3 times the cosine of 3t. And y double prime would be, well, minus 9 times the sine of 3t after the differentiation. So I think you can see it right away that y prime prime plus 9y is, well, in this case, it's minus 9 sine 3t plus 9 times sine 3t. And again, that's equal to 0. So we have another solution. Okay, I think I'm going to leave, well, maybe I should do it, but my last example here is about the general solution. Maybe I need to move it up a little bit to give myself enough room. This expression, c1 times sine of 3t plus c2 times cosine of 3t, I claim that's a solution to this differential equation for any constants c1 and c2. So this is what I would be calling the general solution. There's a big story here, but just kind of roughly speaking, just to let your brain catch on to a pattern, the general solution to this differential equation has 2 constants in it because the differential equation had a second derivative in it. Sometimes people use the word order for the highest derivative. So this is an order 2 differential equation. Okay, so an order 2 differential equation in general will have 2 constants in its general solution. So here, let's just do it real quick. At least let's compute the derivative. So if we compute y prime, I'm looking at this expression up here that I've outlined in yellow. And remember, c1 and c2 are just constants. So the derivative of c1 times the sine of 3t is 3c1 times the cosine of 3t. And likewise, the derivative of that second term is minus 3c2 times the sine of 3t. Okay, so then differentiating again, we're going to get minus 9c1 times the sine of 3t. We're going to get minus 9c2 times the cosine of 3t. So that chain rule spits out another 3, making those 3's 9's. And then here, I'm not going to write it out, but I think you can see if you take y prime prime, okay, and you add it back to this y, look, or not, excuse me, 9 times y. Let me at least write that down here. So 9 times y, I'm looking at the yellow highlighted thing at the top, that's 9c1 sine of 3t plus 9c2 cosine of 3t. And I think with those things stacked on top of each other like that, we can see that if you took that second derivative and you added the 9y below, you're going to get 0. Yeah, because you have minus 9c1 sine 3t and it's plus. So together those give 0. And here you have negative 9c2 cosine and it's plus. So together those give 0. All right, so that thing solves that differential equation for any value of c. c1 and c2, any values. This notation right here, I didn't say anything about it. This just means c1 and c2 are real numbers. That's how you can read that. Nice. A lot of your homework is going to be this. Verify a given function is a solution to a differential equation. So it's kind of a differentiation assignment together with plugging in to make sure some equation is satisfied. Some differential equations we can solve just by integrating. Okay, not all differential equations, but if the differential equation has the form that the unknown derivative to the first power is just some function of the input variable, then finding a solution to this means integrating. Yeah. So in fact, I mean, all throughout chapter 7, if you like, in this language, what I was showing you how to do is find solutions to differential equations. You were finding solutions to differential equations of the very special form where some function's unknown derivative was given. And then how did we find that function? Well, we integrated that thing. Yeah. So the process of integration is solving differential equations of this form. So look here, we can do it. If y prime is x to the fifth, then the unknown function that we're looking at is the integral of x to the fifth with respect to x. Okay, well, the integral of x to the fifth with respect to x is 1/6 x to the sixth, and then plus our constant, yeah? So this is our general solution. The general solution to that thing is that y of x is 1/6 x to the sixth plus c. Okay, so now I'm going to sneak in some more vocabulary on you. I specified that I wanted to solve this differential equation subject to this initial condition. An initial condition is just a certain value of the function for a certain input value. So I want of this family of functions, this infinite family of functions that solves my differential equation, I want the one that passes through the point 0, 11. Okay, well, if I use that initial condition, what does it mean? It means replace x with 0 while you replace y with 11. And that, in this case, it determines that the value of c would be 11. So the solution to this thing that satisfies that initial condition is y of x is 1/6 x to the sixth plus 11. Okay, I'm going to throw some more vocabulary in on you. It's going to be sort of messy when I write this, but a problem like this, finding a solution to a differential equation that satisfies a certain initial condition is called an initial value problem. An initial value problem. We just solved one. We'll use the acronym IVP from now on. So an initial value problem, let me just say again, consists of a differential equation together with an initial condition. And solving an initial value problem means finding the general solution to the differential equation. We did that here by integration. In general, it's a whole subject. We're gonna just kind of taste how to solve differential equations in this course, but for this one, we could do it by integrating. So finding the general solution by integrating, and then using that initial condition to determine the value of the constant that satisfies it. Okay, so this thing down here, I would call the solution to our initial value problem. And again, kind of a mathematician's definition of what scientists do. Scientists solve initial value problems because out in your observations in science, you can observe some rate of change. So what you're watching will lead you to some differential equation. And then you've usually made some measurements. You usually know the quantity that you're studying at least somewhere. You know some initial condition. And you're trying to come up with a way to understand what that quantity will be in the future, if you like, if it's a function of time. So you're trying to solve an initial value problem. Cool. Okay, so I'm going to end this video lecture just by kind of talking a little bit more about the relationship between differential equations and science by making the following observation that many so-called laws in subjects like physics, chemistry, biology, geology, whatever your flavor is, any kind of science, many of these so-called laws, and I'm just saying so-called because that's a term that people use, from a mathematical point of view, these laws are just differential equations. So I want to look at a couple of examples here from different branches of science in which we take some law that's written out in some form. I'm going to start with one from population biology, and I want to just kind of translate it into a differential equation. Okay, I'm going to translate these laws into differential equations. So here's my first one from population biology. So the law that I'm stating, and I'm not asking you to kind of verify the truth or falsehood of these laws, take them as givens. Okay, and all I'm trying to do is, given that this statement is there, how would I write it down mathematically as a differential equation? So the law is that the rate of change of the size of a population is proportional to the size of the population. Okay, so buzzwords here: rate of change, it's derivative, right? The rate of change of the size of a population is proportional to the size of a population. So the rate of change means it's a derivative. So that's why this is a differential equation. It's saying that that rate of change is equal to something. So that's why it's an equation. And then this part is telling us, well, what it's equal to. It's proportional to the size. So let me try to start giving some notation here to write that down mathematically. Let's say that this population is, say, described by a function p of t, and let's this thing be the size of the population at time t. I'm going to suppress the units here, but maybe it's time equals t in hours if this is a population of bacteria cells, or maybe it's t is equal to days if it's a population of rabbits or something that you're breeding, or maybe t is equal to years if it's a population of blue whales. The time unit could be appropriate to whatever you're studying, but let's just say that p of t is the size, so the number of individuals in this population at time t. Okay, then how can I write down the rate of change in the size? Well, that's a derivative. The rate of change in the size is the derivative. I'm going to use Leibniz notation here instead of just writing p prime. So I'm going to write dp dt. Okay, dp dt is the rate of change of the size. So our differential equation says that that rate of change, dp dt, is proportional to, remember that means it's a constant times the size of the population itself. Okay, so there is our differential equation. This differential equation, mathematically, I'm just going to kind of highlight when I say it, mathematically, it says that the rate of change of the size of a population is proportional to the size of the population. So in the notation I was using above, I would just write something like, oh, that's the differential equation, p prime is equal to kp. Or in my first example, y prime is equal to k times y, right? So we kind of even have an idea of what the solution to that equation looks like. And I'm just translating it into a differential equation. If I knew the initial size of the population, if I had an initial condition, I'm using an acronym that I didn't define above, but initial condition, maybe I know the size of the population at some initial value. When I started studying it, I could count how many bacteria or how many rabbits or how many blue whales I had. So P0 is this initial size. So I'm not going to do it right now, but solving that initial value problem would be tantamount to being able to predict the size of this population at any time t. Okay, so that's kind of what population biologists like to do. They like to be able to say what a population is going to do as a function of time. So they're looking at a certain differential equation. This is a particular model of it. So there's certainly some assumptions involved here, but I'm just trying to give you the gist of the mathematical idea. Here's an example from physics. It's called Newton's law of cooling. I'll just read it with you here. So Newton's law of cooling says the rate at which the temperature of an object changes is proportional to the difference in the temperature of that object and the temperature of the surrounding environment, the so-called room temperature. Okay, why is this a differential equation? Well, look at that. The rate at which the object's temperature changes. That's a statement about derivative, right? What are the keywords? What are the buzzwords? Rate, changing, derivatives. It's another one, it's proportional to. So there's going to be some constant, but this time it's proportional to the difference in the temperature of the object and the temperature of the environment. So if I were to give some notation to write this down as a differential equation, I might do something like this. Let's let T, capital T of T, be the temperature at time T. I'm going to be brief here so the video doesn't get too long. But again, I'm going to leave out units, but maybe capital T is measured in Celsius and little t is measured in minutes or hours or something like that. But I'm just going to let T of T equal the temperature at time T. And then there's another constant, the room temperature. So I think I'm going to denote it by something like T sub R. R is for room. So T sub R is the room temperature. Okay, so how could I write down Newton's law of cooling as a differential equation? It's saying that the rate of change in the temperature, it's understood with respect to time of this object. So yeah, T of T is the temperature of the object at time T. The rate of change in this temperature, the temperature of this object at time T is proportional to, that is a constant times, the difference between the temperature of the object and the room temperature. Okay, so Newton's law of cooling stated as a differential equation exactly looks like that. Here K is some constant. So that's how I would write down that physical law as a differential equation. Cool, right? If you knew the initial value, of that object, then finding a solution of this differential equation subject to that initial condition, that is solving this IVP, would be equivalent to being able to predict the temperature of this object as a function of time. So that's something you might want to do. All right, one more. Also one of Newton's laws. Newton had a lot of laws. You can tell I have kind of an affinity for physics. Maybe in a classroom discussion or an office hours discussion, you could ask me in your discipline. Maybe you're a computer scientist. Maybe you're a geologist. Maybe you're an engineer. And there's differential equations in every subject. So we should talk about some. But here I'm going to end this video with Newton's second law. Newton's second law says that the force acting on an object in motion is equal to the product of the object's mass and the object's acceleration. So this one's a little harder to see why it's a differential equation, because there's no rate involved. At least the word rate itself doesn't appear. But let me remind you that if we say denote by S of t the position of some object at time t, again, suppressing all units, but this is an object, say, moving along a line. So it's the position of an object at time t on some line, on a number line. So simple linear motion. Then the second derivative of that function is the acceleration. Right? Second derivative of position. First derivative of position is velocity. The second derivative of position is acceleration. So if we denote by, say, F is the force, and say little m is the mass of the object, suppressing all the units, then Newton's second law is just the differential equation that force is equal to mass times acceleration, the second derivative. So if the force is known at all times t, then you can try to solve this differential equation. Solving this differential equation is tantamount to locating the position of that object at any time t. All right? And you might say, well, how would I possibly know the force on this object in motion? Well, in certain circumstances, you do. Like, for example, if the motion is just falling, capitalize our planet, falling on Earth, then the force is a constant. It's negative 32 feet per second squared, or negative 9.8 meters per second squared. Yeah, it's the acceleration is a constant. The acceleration is a constant on Earth. So in other words, we know that force, it's the force of gravity, right? So solving that differential equation is basically tantamount to determining where this object is at any time t. And in this particular example, we could do that by integration, right? So if s prime, let's use the units in feet and seconds. So if we were going to try to solve this thing, well, I could say, well, s prime is the integral of s double prime with respect to time. And that's negative 32 t plus some constant, right? And in order to determine that constant, I would need some initial condition. I would need to know the velocity at a certain value of time, right? And then we could integrate again. Let me call this constant c1. We could integrate again, so we get negative 16t squared plus c1 of t plus some other constant. Okay, so we could determine c1 if we know, say, s prime of 0, the initial velocity. We can determine c2 if we know s of 0, that is the initial position. And hopefully this all sounds familiar. This is stuff you did in Calculus 1. You can recover the location of a falling object if you know its initial velocity and its initial position. And this quadratic equation should probably look pretty good. So this solution to this differential equation looks pretty familiar to you. Okay, so just to summarize out loud what we did here today, let's make a little summary. We talked about what a differential equation is. We talked about what a solution to a differential equation is and how to verify one. That's the main part of the lecture, okay? At the end, we were just sort of translating physical laws into differential equations. And that end part was really just sort of to make you excited and interested because you guys are, well, some of you are mathematics majors, but most of you are majoring in science for which your mathematics is a tool to do what you really want to do. Differential equations is a pretty exciting tool. Okay, so thanks for listening.